Good morning, dear students. Today we will be discussing the theory of holography. We will mathematically derive it also. Then we will discuss various types of holography methods, configurations, and technologies. And then we will discuss applications. Although we have discussed about holography and the importance of coherence in the previous video and in the earlier classes, but I will uh, touch those also uh, more as a let's say remembering for the uh, upcoming topics. So let's start. Uh, so The topics are already covered here: principle of holography, characteristics, recording, reconstruction, classification, and one of the major applications is non-destructive testing that we will discuss. But before we do anything, let's first understand the basics of the uh, holography uh, working. So as you can see here, this is the object, and normally when you take a photograph of any object, the photograph is recorded on a plate. The light coming from the object is uh, recorded on the plate in the form of intensity in x and y direction. That's all. So this is a photograph, and there is no information about the third dimension, and that is depth. That means if you are looking at my image, you only see the photograph of my front portion. You are not able to see the depth. Like if you see this surface, you are not able to see the other surface or the surface behind this area, even from another angle. So that means the distribution of this photograph is in two dimensions only. If we want a three dimension then photograph, then we will call it holograph, not photograph. Holograph is a uh, method or a recording which will include not only the distribution of intensity of light of the object in xy plane, but it will also include phase information in the z direction, phase information about the image, about the object. So how do we record the phase information? So one of the ways which is identified and was discovered by Gaber is that if you put a reference wave, another light source, coherent light source, as a reference wave, and allow this coherent beam to fall on the same recording plate where another light wave is, or coherent light wave is coming from the object. These two waves, the waves coming from the reference source and the waves coming from the object, when they interfere, then the destructive or constructive interference will occur depending upon the phase difference, right? And that will cause formation of fringes. Right? And those fringes, interference fringes, are governed by the phases. So you get the information about the phase. So once you get the information about the phase as well as about the intensity of light distribution of the image, then you are going to get the three-dimensional picture from different angles of viewing, right? So that was all about this one. Now I will show you a so uh, so here the idea was that you see a live explanation about how a hologram works and how the reference beam and the object beam interfere with each other. Now, uh, now we go to the theory of the holography derived mathematically. So let's start with the uh, uh, with this. This whole derivation has been taken from the book of Ajay Ghatak, uh, and you can refer to that book from the library also. Let's start. Uh, See, as you can see in this photograph, uh, there are two sources of light. One is from the object and other is from the reference wave. Now, in order to understand this interference and derivation, let's first look at the basic example of uh, a, a superposition of waves. In your during your undergraduate studies, you might have studied the derivation of intensity of light wave because of interference between two light waves. So let us assume that one wave is y1 equal to a1 sine omega t, the other wave is y2 equal to a2 sine omega t plus delta, where this a1 and a2 represent the amplitude of the component of the individual beams, whereas omega is the frequency of the light wave, both are coherent, and delta is the phase difference between the two. Now, if you superimpose the two, then the resultant wave y will have these two waves, and if you solve them, you will finally get a equation which is represented by this equation. And as you can see clearly, this theta, this includes the phase difference between the two, right? And r is the resultant amplitude of the two amplitudes of the two waves, that is a1 and a2. R is the resultant amplitude, but it includes now information about the phase also. So finally what we get here is the resultant wave having an amplitude r, right? And this r amplitude consists of the phase information as well, so that is critical. And also the the resultant phase, which includes the initial phase of the second wave also. So that way what we are saying here, that in an interference pattern you get the phase information as well as the resultant intensity information. And finally when you calculate the intensity of the resultant wave, this will be equal to r square, that means resultant amplitude square, which will include the amplitude of first wave, then amplitude of second wave, and then 2 a1 a2 cos delta, that is the phase between the two. Now I just give an example so that you can correlate it with the mathematical derivation which we are just going to discuss. So let us, you can go into the details of the two waves, but I will restrict myself to the two basic things. One is the first object wave, like this y1 equal to a1 sin omega t is oxy, and this wave. Now here the difference between the two is that in this particular example you are considering a point source, but whereas you are considering an object from where the light is distributed in x and y direction. So the light coming from the object is a function of x and y, so its amplitude, yes, it will have amplitude distribution in x and y direction, and then cos phi minus omega t. So this represents the object wave. Only difference with this one is that it has a distribution in x and y direction. Now, the second reference wave, since it has to include the information about the depth also, so we consider it as r, x, y, and z direction, and this is given by similarly a, which is again will be a function of x, y, z, and cos k dot r minus omega t, which we can define here as this one. Now, K is the wave vector, as you already know. Now, if I take the resultant of the two, of course, this equation has been simplified to this form, assuming that we are taking a image at z equal to 0 on the photographic plate. So this equation will reduce to this one, right? Now if I take the resultant of these two waves, this wave as well as this wave, then you get a resultant wave equal to the sum of these two waves, right? And the intensity will be the square of the resultant amplitude. Like here, the intensity will be the square of the resultant amplitude, and this will be given by this one. See, the amplitude of the first wave, the amplitude of the second wave containing the phase information, and this 2a1 a2 cos delta, like this. Now, since we are talking about at z equal to 0 plane, so we are ignoring z, and also we are taking the averaging out of the first wave, that is the first wave here, and the second wave, that is the second wave here. So we consider it half, and the third one, this term, if you simplify trigonometrically, then this will be reducing to this one, because this is something like cos A cos B, that is equal, that you can relate with a formula, a trigonometric formula, that is cos A minus B equal to cos A minus B equal to cos A cos B plus cos A sin A sin B. And since sin Z will be 0, theta will be 0, so that term is ignored. So you get this one. Finally, you get the equation of intensity, where the amplitude of first wave, amplitude of the second wave, and the combination of the two amplitudes to cos is defined like this one. Right? Now, if you look carefully at this equation, then you find that this equation has three terms: the first term, second term, and the third term. Now, this will be explained further, but before that, I just want to tell you that if you want to, this is as far as the recording of the intensity is concerned on the recording plate. Now, if you want to reconstruct it, because you want to see the transmitted image from the field, so you consider a transmitted field, and this transmitted field is equal to, K, and then the resultant. K is a constant, and this resultant will consider these parts. So, this transmitted field will have the three major components: first one this component, the second one this component, and third one this component. If you look at this carefully, you will find that the first term represents one particular type of term where the amplitude of first and second wave was involved. Then the second term considers only the amplitude of the reference wave, right? And the third term consists of the amplitude of the reference wave, of course, that one, but it considers the z direction also. Now, we'll just explain it here. This equation 11 gives the transmitted field in the plane z equal to 0, and the first term, as we mentioned here, first term is nothing but the reconstruction wave itself, whose amplitude is modulated due to the presence of the term a square. This first term, this one, right? So, similarly, if you look at the second term, this is identical to the right hand side of equation 1. The first one is, if you see, so that means this one. So this considers the amplitude of the reference wave itself, right? And the third wave, the third term, is giving you the complete information about alpha phi, that is the first phase of the first wave, as well as the uh, phase in the z direction. So that means this gives you the complete reconstructed image, this the, the virtual image, and this is the total image, real image. Now, uh, this is what explained here. So I will not go into detail, but what I am going to mention here is that these three terms in this equation represent the three type of images which you see. One is the real image. The real image is this one. Then the virtual image, and then the third one is the reconstructed image. And all the three are important. Now, if you want to record and reconstruct, so just the procedures are given here. Recording you have already seen. For reconstruction, you simply have to put the laser source uh, again from the same position from where the reference wave was given, and then you will find the virtual image in this direction and the real image is this direction, and you as an observer are sitting here, so you will observe the virtual image at this location, right? So this is how the uh, uh, reconstruction process works. Now we'll be discussing the classification of holograms. So we'll just wait here and we'll go for the uh, next class. So till then, goodbye.